All right, let's dive into the microscopic battle that's literally shaping the future of all technology. FinFET versus GAAFET. Now, I know these sound like crazy acronyms, but stick with me, because these are the tiny, unbelievably powerful switches at the heart of, well, everything, from the phone in your hand to the massive data centers that run our world.
This right here is the multi-trillion-dollar question. It's what drives the entire semiconductor industry. For decades, the answer seemed pretty simple, right? Just shrink the transistors. But eventually you hit a wall, a physical limit. And at that scale, things start to get really, really weird.
So here's the problem. As those old-school flat transistors got smaller and smaller, they stopped being perfect on-off switches. They started acting more like leaky faucets, just dripping electricity, wasting power, and creating a ton of heat. This leakage was a huge barrier to progress. To keep things moving, to keep Moore's law alive, engineers knew they had to think differently. They had to start building up. And that's when our first hero entered the scene, FinFET. Instead of just a flat 2D design, engineers went vertical. They created this revolutionary 3D structure that just completely changed the game.
Think of it like this. An old transistor tried to stop the flow of electricity by just pressing down from the top. Kind of weak, right? But with FinFET, the gate, the part that acts as the switch, wraps around the channel on 3 sides. It's like going from a one-finger push to gripping a pipe from the top and both sides. All of a sudden, you have so much more control. This tri-gate structure was, no exaggeration, a total game changer. It slashed that annoying leakage, which meant way better performance and power efficiency. This design quickly became the workhorse of the entire industry, powering our world as we scaled down manufacturing processes, what we call nodes, from 22 nanometers all the way down to 5 nanometers.
And hey, this isn't some far-off lab experiment. The device you are using to watch this right now, it's almost certainly packed with billions and billions of these tiny FinFETs. It is the unsung hero of the last decade of tech. But as we keep pushing the boundaries of physics, even heroes eventually meet their match.
So as we tried to push beyond 5 nanometers and down toward 3, even the mighty FinFET started to show its limits. That leakage problem started creeping back in. To get even more control, engineers needed a whole new architecture, one that could go, literally, all around.
Okay, so if FinFET was like gripping the channel on 3 sides, GAAFET is like making a complete fist around it. The gate material fully surrounds the channel on all 4 sides. It gives engineers this ultimate 360-degree control over the flow of electricity. It's about as close to a perfect leak-proof switch as we can possibly get right now.
So what does this all-around control get us? Well, it means even less leakage, which leads to better performance and, crucially, a clear path to scale below 3 nanometers. What's really cool is how they're built. Instead of a single vertical fin, GAAFETs often use these stacked horizontal nanosheets, which gives chip designers a ton more flexibility to fine-tune performance.
Okay, so we've got our 2 champions. On one side, the established king, FinFET. On the other, the new challenger, GAAFET. Let's put him head-to-head and see how they stack up.
When you boil it all down, the core difference is just this: 3-sided control versus 4-sided all-around control. That one extra side of contact might not sound like much, but it's the fundamental advantage that unlocks the next generation of computing. It's a simple geometric change with absolutely profound consequences.
Looking at them side by side, the trade-offs become really clear. GAAFET, no question, offers higher performance and gives us a roadmap to future nodes like 2 nanometers and even 1 nanometer. But that power comes at a price. It is way more complex and expensive to manufacture compared to the FinFET process, which has been perfected over the last decade.
So what does this all mean for us? For the future? Well, this shift from FinFET to GAAFET isn't just a small step. It's a huge leap that's charting the course for the entire future of computing.
You can really see the evolution right here. We went from those flat 2D transistors to the 3D FinFET era, which gave us an incredible decade of progress. And now, as we enter the 3 nanometer age and look even further, we are officially in the GAFF future.
So why should you care? Because the next big thing, especially in areas like artificial intelligence, requires an absolutely insane amount of computing power and efficiency. GAFAD is the engine that's going to make it all possible. It's what's going to enable more powerful, more complex AI models to run right on our own devices.
And look, the consensus in the industry couldn't be clearer. As one source puts it, gate-all-around represents the future of transistor architecture for advanced technology nodes. For the most cutting-edge chips, gate-all-around isn't just an option, it's the designated path forward.
So let's just boil this all down. FinFET was the amazing 3D revolution that saved us from the leakage crisis of the old flat transistors. Now, GAAFET is taking it to the next level, offering that ultimate four-sided control we need to build the chips that will power the AI revolution and whatever comes next.
And that really leaves us with an exciting thought to end on. Every time we get better at controlling these tiny, tiny switches, we unlock things we could barely even imagine before. In medicine, in science, in communication. So with this new level of near-perfect control, the real question isn't just what's possible, it's what incredible challenges are we going to solve next?